In this video we're going to explore some problems from 11.5 in your book, and we're going to do an area of a sector, an area of an annulus, which is the shaded parts of concentric circles, and then we're going to find the probability of a point being in that shaded region. Then we'll find the shaded part of, it says hexagon here, but really it's a pentagon in the example. It's a mistake right there. In a circle, where only some of the, not 6, but 5 segments are shaded. We're going to find the probability of a point being in that shaded region. And then we're going to find the area of a segment and find the probability of a point being in that shaded region. We're going to review how to find the area of an equilateral triangle given the perimeter, and then an area of an irregular figure, an area of a shaded region of just a random type of figure. So I want to encourage you to use this video to look at specific examples that you're struggling with. It'll be a longer video than the introductory ones before we cover a topic in class. So in this first problem we're going to find the area of a sector. And in the area of a sector we're finding a fraction of a circle. So in order to find the fraction of the circle, we use the degree of that central angle or intercepted arc of the central angle, which will be the same measure. And we'll write a fraction over 360. And then we'll take that fraction and multiply it by the area of the circle. So it gives us the fractional part of the circle for that area. So notice we have 80 degrees over 360 times pi times 5 squared, and I'm reducing here. I'd like to look at those zeros and get them out of the way in my head first, and then we know that 4 goes into 8 2 times, and 4 goes into 36 9 times, so that's where 2 ninths came. 5 squared is 25, so we're going to write 25 pi here. Multiplying that out gives us 50 pi over 9. And we're going to leave our area there with centimeters squared as our units. There's no reason to change that to a decimal at this point because we don't have any other purpose for that problem. So leaving it as 50 pi 9 over 9 gives us an exact answer rather than approximating it. In the next problem we're going to find the area of the shaded region, and we have an annulus here. That's a bunch of concentric circles, and notice we have the biggest circle is shaded and then the one in the middle. So in order to find this one, we're going to actually find the area of the large circle minus that middle white circle and then add back the small circle. And then that will help us get the total area. Now if you look at the radius of that large circle that I just drew in, the radius of the small circle is 1 because it shows you the diameter of it is 2. And then each of the circles are spaced 1 yard apart. So you're going to see that we have a radius of 3 for the large circle and a radius of 2 for the small. Let's go ahead and find the area of the large circle using pi times 3 squared. Then we'll subtract the middle circle. And so in that one we're going to use pi times 2 squared. Then we're going to add the small circle back in, and that is going to be plus pi times 1 squared. And then we can simplify those, so that gives me 9 pi minus 4 pi plus 1 pi, and then we'll combine our like terms to get 6 pi. Now I'm going to leave it like that for my shaded area. Again, that is one instance where we don't really have a need to change that to an approximation for a decimal, and then we'll change our answer a bit when we do our probability. We're going to get an exact answer here, an exact fraction when we find the probability. Now to find the probability, you take the whole area, which happens to be that large circle, and if I want to know the probability of a point in the shaded area, then you take the shaded area we just found and divide it by the whole thing, which is that large circle. So that's what we're going to do here. We're going to take that probability of the shaded will be out of the total, which is 9 pi. We'll take 6 pi. So 6 pi divided by 9 pi. Pi's cancel out. 6 over 9 reduces to 2/3. So my probability of a point lying in the shaded area is 2/3. Now in this problem we have a regular pentagon, and to find the shaded area we're going to take 3/5 of the difference of those two. Now, why 3/5? Normally, if all of those segments were shaded in that circle after the pentagon covered the circle up, we would take the area of the circle minus the area of the pentagon. But only 3 out of those 5 segments are shaded, so we'll take that fraction of it and take 3/5 minus that area that we find. Now I want you to notice that 15 is shown as the length from the top of that circle to the bottom of that circle, which means our radius then is 7.5, half of the diameter. So let's put that in the radius in our picture, and then we're going to find that angle right there, which you see I marked up as 36 degrees, in that right triangle formed by the apothem that's dropped from the center of that pentagon in the center of the circle. Now, how is it 36 degrees? Let's remind yourselves that the central angle is found by taking 360 divided by how many central angles you have. And that gives me 72 degrees. Now, we're only interested in half of that central angle. The full central angle, remember, goes from the center to 2 points on the circle. And notice where that big triangle lies. So we're interested in just the half that is formed by the apothem. Remember, the apothem cuts that central angle in half. So we'll take 72 and we'll divide that by 2, and that's where we got the 36 degrees. That's just a review. Now we're going to find the area of the pentagon, and remember, it's regular, so we use 1/2 a times p. Now I need to find the apothem, and I need to find the perimeter. So I've marked up my apothem with that a, and I'm going to call each piece of that side. Remember, the apothem cuts the side in half, so I called each piece of the side that was cut in half x. And then when I want to find the whole side, I'll take x and just add those 2 x's together or multiply by 2. So let's start by finding the apothem, which, if you notice, you have the 36-degree angle. The apothem A is the adjacent side to the angle, and we know the hypotenuse is 7.5, so that's a cosine ratio. So we're going to write the cosine of 36 equals opposite A over hypotenuse 7.5. Multiply both sides by 7.5, and then put that into your calculator, and that's going to give you 6.07 equals A. Now we're going to do the same again for the x, and that happens to be a sine function. So notice I put sine 36 equals x over 7.5 because x is the opposite side to the 36-degree angle, with 7.5 being the hypotenuse. Sine is opposite over hypotenuse. So I've got my sine 36 equals x over 7.5 written down, and I'm going to now multiply 7.5 on both sides. So the 7.5's on the right will cancel out, and I'm going to put that in my calculator to get 4.41 equals x. Now, why am I multiplying 2 times 4.41? Remember that the side has got 2 of those x's there because that apothem bisected it. So my side length is actually going to be 8.82, and then I can multiply that by 5 to get my perimeter, since all those sides will be equal. So 5 times 8.82 in your calculator will give you 44.1. So now I'm ready to find my area. I'm going to plug those numbers in. 1/2 times 6.07 times 44.1. And when I multiply all that together, I'm going to get the area of that pentagon is 133.84. I didn't give you any units, so we're just going to say units squared. Just clearing up the field here so we can now get the area of the circle. So the area of the circle, remember our radius is 7.5, so pi times 7.5 squared. And when you put that in your calculator, I am going to go to a decimal this time because I have a decimal from my pentagon. So I got 176.71. I'm going to take 3/5 times 176.71 minus 133.84. Put all of that in my calculator. So when I did that, I subtracted 176.71 minus 133.84 first, multiplied by 3, and then divided by 5, and got 25.72. And now notice I'm clearing the field here again to get my probability of my shaded area. I'm taking 25.72 and dividing it by 176.71, and that will give me a probability of 0.15 or 15%. Now, why did I take 25.72 divided by 176.71? Remember that we just found the area of the shaded to be 25.72. I want to find the probability of a point being in that shaded area. So I took the shaded area, divided it by the total area, which is the circle. The circle represents the entire area. So that's why I took 25.72 divided by 176.71. So your probability again was 0.15, or if you prefer to call it a percent, 15%. Now we're going to find the area of a segment of a circle. And notice the segment is formed by a sector and a central sector, and then the triangle, that chord that makes the triangle. So you've got that chord, and the chord goes from here to here, and it's formed by that sector. So that's the purple that you see. But let's go ahead and get rid of that because I really don't want all of that in my picture. Notice you have from top to bottom is 16, so you're going to have a radius of 8. Okay, so to find the area of that segment, we're going to take the area of the sector, we're going to subtract the area of that triangle, and we have a radius of 8. So we're going to find that central angle, and I want you to remember that we have a regular triangle here is what we're dealing with, and so the central angle is going to be 360 degrees divided by 3. Since there's 3 sides in a triangle, there will be 3 central angles. So CA for central angle, so 360 divided by 3 is 120 degrees. That's going to help us find our sector. So let's just mark that in our diagram. So the area of the sector will be 120 divided by 360, that's our fractional part of our circle, times pi radius squared, in this case it's 8. And then when reducing that, the zeros cancel, you can see you have 1/3. 8 squared is 64 pi. So I get 64 over 3 pi. I'm going to leave it like that for now, but this one I'll probably have to convert. I'm going to go ahead and just take that 64 over 3 pi and put it up here for my sector. Clearing the field to look at the area of that triangle now. And notice I've redrawn the triangle. So, and the triangle that you're looking at is the triangle that is formed by the chord and the sector. So the radius is 8, and so that's going to be the side, one of the sides of the triangle. And I'm actually forming a 30, 60, 90 triangle. Well, that's because I have to take half of that central angle again, and that's how I got the 60 there. Now, 8 is the hypotenuse there for that 30, 60, 90 triangle, and the side across from the 30 is the short leg, so it'll be half of the hypotenuse, which means the side across from the 60 to be the long leg, which is 4√3. So notice that the whole base of that triangle is 4√3 plus 4√3. So I can use area equals 1/2 base times height, and notice I put in 8√3 for the base. The height of that triangle is 4. So we'll reduce those, the 2 and the 4, to get 2 on top, so that gives me 16√3. So I'm going to put that up here under my triangle. So the area of the segment then, if I take 64 pi of 3 is 67.02 in my calculator, and 16√3 is 27.71. That gives me, when I subtract those, area of the segment is 39.31, and that's units squared. Here's some review problems. We did some irregular figures way back in the beginning of the school year. Let's look at another example.